Hello everybody and welcome to Science Live. We're coming to you today from the Creation Museum in Petersburg, Kentucky. As you probably noticed, we're not in the lab, we're not in Discovery Hall, but we're outside on the patio overlooking the deck because today we're going to be doing some exciting stuff that we probably shouldn't be doing inside of the classroom or inside Discovery Hall. We'll be launching some rockets. So I've got our physicist expert with us today, Dr. Danny Faulkner. He's joined us to help us understand some of the physics behind what's happening, and I'll be talking about the chemistry, and we'll be looking at a lot of different exciting things today. We're doing some interesting testing today on streaming this in different ways to different platforms, so we hope you'll be able to connect with those things. I'll be following along on Ken Ham's Facebook page, looking for comments, so if you've got questions or anything you'd like to ask, we will be observing those things and trying to engage with you there. So drop your name, drop your age for you kids, and we'll try to answer those questions for you. All right, Dr. Faulkner, what is, if you think about rockets, why do you like rockets so much?
Oh, they burn, they explode, they move, they take off fast, they go places. It's just, if you're a little kid and you comes out, it really does.
So you're like a 10-year-old little kid just trying to blow up some rockets and launch things and have
hopefully
fun with
not hurt anybody in the process.
Yes, but our whole goal here is not just to make stuff explode, but we want to show you some of the principles behind these things, and the ultimate goal is to show you that all of these things are possible because of how God has organized the universe around us in predictable ways with physical laws that are understandable and relatable. So the basic concept we're going to be talking about today is propulsion. So there's your big science word for the day. When I say the word propulsion, you might think of propel. That's moving something forward, and there's lots of ways we can do that. So we would think of words connected to that from motion words of physics like momentum, force,
acceleration,
velocity, acceleration. We did a program a few weeks ago looking at the marble track and how force and mass and acceleration are related to those things. So we're going to be looking at a lot of those different things today. The other principle is the conservation of mass and energy. So why don't you take a minute and explain what that law of conservation of mass energy talks about and kind of relate that to the idea of rockets.
Okay, when we do experiments, we measure up masses, how much matter something has. And chemically, physically, no matter what we do to them, if we don't allow any new matter to come in or to leave the system, the entire amount of matter we have remains the same. If you start with, say, 1 kilogram of matter, we will end up with 1 kilogram of matter. And this thing was discovered probably in the 1800s. They called it the conservation of mass. Also in the 1800s, they discovered this principle of conservation of energy. You have so much energy there provided, and that energy is also conserved. If you start with so many what we call joules of energy, if you don't add any or take any away from your experiment, then you'll end up with the same amount of joules of energy at the end. Now today, about 100 years ago, Albert Einstein unified energy and matter, and he discovered that there's an equivalence between the two. So now we think of the sum total of mass and energy together being conserved. But for most applications like we'll be doing today, we can keep conservation of mass and conservation of energy separate from one another.
All right, we've got people joining us from all over the country, and I see, just as we mentioned, that Nancy and Craig and others are definitely interested in this, and they're all over 50. They're all dropping their ages in there too as well. So not just
still
for
little kids.
Still little kids inside doing all of those things. Okay, let's take a simple object that you all have around the house probably, or you've all experienced before. Just a rubber balloon or an elastic balloon here, and we think about the conservation of energy. So right now we'd say in this balloon there's virtually an equal pressure to the air around it.
Yes.
So we've got a balance of pressure inside the balloon and outside the balloon, so it's basically collapsed. I can use this pump and I'm going to transfer energy from the food that I ate for breakfast this morning into the chemical energy there into a mechanical motion in my muscles that's going to transfer into friction and mechanical motion here inside the pump, and the piston's going to go back and forth, and that's going to force air, force meaning we're applying energy, applying a force to this, into this balloon, and it should increase the pressure.
And the balloon stretches and gets larger, but there's pressure inside of it.
Okay, so we've got pressure inside of this balloon that's greater than the pressure on the outside. So what happens in systems where there's a greater pressure and a lower pressure?
Well, the greater pressure wants to move towards the lower pressure. That's just one of those things that happens. They want to balance out if it can. Well, right now it can't because you've got the thing sealed up at the end here, and you've got it being contained by the elastic in the balloon.
Okay.
But if you open it up somehow, pop a hole in it or let it out here, then that air is going to escape from the higher pressure to the lower pressure to balance out that pressure.
And in general, we talk about things in nature like to go from high to low.
That's
Think
it.
about gravity. If I hold a ball up in the air and I drop it, it's going to go from high to low.
Yep.
Okay? So this is a
High pressure to low pressure.
common principle, high to low. Everything wants to reach that state of
Lower energy.
Lower energy. In biology, we call it homeostasis, and we
Physics, you might call it entropy.
Entropy, yeah. Okay, so if I let go of this balloon, we can make a prediction of what's going to happen because the high pressure air is going to escape, and its route of escape is out here through the end of the nozzle, and
there it goes.
it goes for a ride, but in a rather unpredictable pattern.
Right, but it did
because-
go this direction, and that's
Yes.
important. It didn't go that direction.
Yes.
And there's a reason for that, and we haven't touched about this yet, but there's another principle at play here. We call this action-reaction. This is Newton's third law of motion. And that says for every action, there's an opposite and equal reaction. What happened in the balloon is the pressure was here. You open the valve over here at the end of the balloon, and that pressure wants to shoot out like this. Now to do that, the elastic in the balloon pushed on that air to do it. So it's pushing this way with the air, and the air pushes back against the balloon. So while the air goes out this way, the balloon goes off that way. And it propels the air this direction. We didn't see it, of course, it's invisible, but the balloon went this direction. It flopped around, but it basically went my left, your right as you're watching this. And this brings up another principle we call conservation of momentum. You mentioned momentum earlier. Momentum is a little tricky. It's the product or the multiplication of mass times speed or velocity. More specifically, it should be velocity. And so there's a thing called conservation of momentum. If you don't have any net force acting on something, then the momentum won't change. Now, when the balloon started, it had no momentum. The air, the balloon, nothing. There's no momentum because it wasn't moving. Suddenly, this is moving and suddenly that's moving. The reason why is the balloon has a force going this way, which accelerates it, gives it velocity going in this direction, and the air has a force going this direction. But you know what? They're opposite and equal forces because that's Newton's third law. And as it turns out, the momentum of the air in the balloon is conserved. So even though the balloon went this way and the air went that way, the system itself didn't go anywhere. It just divided into two pieces and went two different directions. And that's a really fun aspect of physics, I believe. And many problems we can solve deal with that momentum being conserved in these cases.
And we see all of those things being repeated in objects in motion all around us. It's a universal law as far as we know. We've never experienced that situation where it doesn't work. All right, Jillian, age 5, asks, why do some balloons pop? Well, basically, the molecules that make up the elastic structure in the balloon, usually latex or some form of rubber, is expanding, and at some point they're going to be too weak to hold all of the pressure that's inside. So the pressure that's inside the balloon is much greater than the strength of some balloons are made to pop. Like if you buy little tiny water balloons, they're made out of thinner rubber so that they intentionally pop when you throw them at your brother or somebody. All right. Okay, so let's, from this point on, we're going to put on our safety glasses.
Remember,
and
safety third,
Safety,
correct?
no, safety's first.
It is? Are you sure?
Always.
Oh, that's right. I get them confused. That is safety first. You're right. I'm
Safety
sorry.
first.
Safety first. I'm sorry.
All right.
I always get this numbering wrong.
And just so you know, so we're safe and secure. Another mechanical motion that we could do here, these are little finger rockets. You may have played with these before. These use basically the same principle. We've got energy being stored in this stretchy elastic material, this rubber band here. And if I were to create a tension on this band, I'm storing up potential energy by my muscles pulling back on this. So I'm using the energy again in my muscles to be able to stretch this. I'm storing up potential energy, And when I release this, it's going to be transferred from this potential energy into the energy of movement. And we'll see if I can hit one of those balloons over there. Oh, that was so weak.
That was pretty weak, yeah.
All right,
Let
we'll
me
see
give it
if
a
Dr.
try.
Faulkner can do it any better. Oh, his shot off to the right. So we need some target practice with those. But the basic idea there is we're changing this potential stored energy into kinetic energy. So kinetic energy means?
That means energy of motion.
Motion. So whenever you hear that word kinetics in anything that you're talking about, that's the motion principles.
And when you stretch that that rubber band on that one, the more you stretch, the more potential energy, elastic potential energy you're putting into it. You don't want to stretch it so far you break the
Yes,
string.
we can, just like we can stretch the balloon too far and it
Stretch the
pops,
rubber band too far.
we can stretch that too far. So that's the same principle that would be shooting a rubber
And
band.
dart guns use springs many times to do the same thing.
We could use a spring where we load a metal spring, it compresses it, and a little latch holds, and then you pull a catch or a trigger.
Compression rather than stretching, but it's the same principle.
Same principle.
Elastic potential energy.
Yep. Okay, what's next here? We've got all kinds of fun things to do.
Neat toys.
Another principle over here. Dr. Faulkner, why don't you go ahead and charge up our air cannon?
Okay, just pump it up real good.
This is an air cannon that I've made, and it has a chamber down here that's going to hold air. Don't pinch your fingers. Oh, wait, time out, hold on.
What?
That's really loud and annoying. Why don't you just use the air compressor? It'll be a lot faster.
The what?
That air compressor right there.
Oh, I didn't see that. Oh,
all right.
That's going to be a lot easier.
A lot easier and faster.
Oh, thank you. Appreciate that. That's good. That is noisy, isn't it?
That is noisy.
All right, so this ought to go fast.
This chamber is going to hold compressed air.
Come take a look at the gauge.
We've
Come
got
look
a
at the gauge
gauge
here.
on here. So again, I want to
This
do
is
all
in-
these things safely.
This
We
is
want to know.
PSI, pounds per square inch.
Yep, we want a
So
controlled
it's 0 right
environment
now,
here.
so it's
We're going to add air into there and try and get that up to about 30 pounds, right where
it's
that
30
black line
PSI
is.
right now.
Okay.
Very good.
So this is storing the air. Now we used electrical energy in the air compressor to pump a piston, just like I did inside of this when I used my mechanical,
Like
or
that.
just like the arm motion did
It's a
here.
lot easier using this, though.
It is, definitely. And all of that air is stored in here at a higher pressure. So if there's high pressure in here and a lower pressure out here, if I release this valve, it should open up and send that air out, because high pressure in here wants to go to low pressure out there. So let's load the rocket.
Okay.
So here's our first rocket, and Dr. Faulkner
I'll get to
is
launch
gonna
this, huh?
aim it over there. Make sure you keep your hand away from that valve.
Do I pull it towards me or away from me?
Yes, you're going to pull it toward you as quickly as you can.
Okay, ready?
Aim toward the balloons over there. Off to the right.
Yeah, hit the tree branch. But you get the idea. It took off that direction.
Yes.
And recoiled a little bit, but not much. That's action reaction once again.
Yeah. Okay. So we've got a different type of rocket here. Why would I have put these fins on this rocket?
Yes, kids. We had no fins on the first one and the second one, but this one has fins. What do you think that's going to do? Any ideas out there? Think about it.
I'm going to go ahead and charge our cylinder again. Same pressure. We're going to go right back up to 30 pounds.
All right. And we're going to slip this rocket on here now with fins. Do I get to do it again?
Yeah.
All right,
Sure.
good.
You get to have the fun today.
So what happens now? Whoa! That went a lot farther.
Went much farther, and it might have been a little hard to see in the video.
Yeah.
But we would have expected those fins to act as a stabilizing force. When we watched that first one, it kind of flopped all over
And that
the
slowed
place.
it down as it went through the air.
Yeah, and that creates more air resistance, and that's a force acting against the
Yep.
motion.
But the stabilizer really worked well. It made a big difference.
Yeah, and so if
A lot
we
of
could-
rockets have those.
Yeah, if we could test this and do repeated measurements, and we could maybe film it and watch the wiggle of the tail. We could even use a computer program to mark the degrees of variance from the axis. All those types of things could be experiments that we could do to test different fin shapes and structures. We could test how much drag it creates and slows it down, and does that give us more benefit versus the stabilization. All of those things would be things we could test.
Yep.
But what about Claude?
Claude?
How aerodynamic do you think Claude is?
Oh, he's not very aerodynamic at all.
Let's see if we can make Claude go for a ride.
Got some
How do you
duct tape?
think, I've got a little tape here. You hold Claude,
okay.
I'll get the tape out. We're going to give Claude a little ride. This is pretty much like one of those slingshot rides that you go on. We need more tape than that. At an amusement park. So let's send Claude on a little ride. I did this once. I got to, at an amusement park, it was a propane fueled scaled version of a dragster car, and they launched me out at like 200 miles an hour, and it was very fun. But it was on rails, so I
Okay.
couldn't crash or anything. All right, let's charge up the cylinder again.
All right.
Close the valve. Let's send Claude for a ride, see if he helps the aerodynamics of our rocket.
I don't think it will. See what happens with Claude this time.
Okay, so notice his weight wants to shift the rocket down, so we'll see how this goes.
Claude's no astronaut.
Why didn't he fly as far, Dr. Faulkner?
Well, I think it was the weight was quite a bit. That foam on the rocket's pretty light, and Claude probably weighed several times what the foam did. So more mass, it doesn't go as far. Remember we talked about momentum, and the more mass you have for a given amount of force put on it, that's Newton's second law, you have less reaction coming out of it. So if you want to send things really high up, you need to make the payload as small as possible.
Okay, so you say a payload. If we were launching a rocket up into space, what types of payloads might we have on
Be a
them?
satellite, might
Okay.
be an astronaut. You know, when they went to the moon 50 years ago, they had the Saturn V rocket. At that point, the largest rocket ever built, and it had to send quite a bit of hardware and 3 astronauts all the way to the moon. So it was a pretty big rocket, and they were very concerned. They were milling down thinnesses. They would shave an ounce here, shave an ounce there. Every ounce counted on that mission.
Yep, absolutely. All right, so Craig's asking you, the old rubber band airplanes work on the same principle. So
Oh,
I
yeah.
think of the balsa ones with the propeller that you
You spin
twist.
it around, you let it go, and it pushes
Yep.
pushes against the air, and the air goes forward.
Yeah,
Or
so
actually
there you're,
pushes it and
pushing it
reaction.
and goes the opposite way. Okay. Okay, so Claude was not hurt in the filming of this. He's just a plastic lobster, so I hope nobody was offended by that. We're just having some fun with Claude. Okay, so another way we can do this is by generating gases. So if we come down over here,
Now you're getting into chemistry.
now we're getting into chemistry.
That's
You
your
might want to
department,
move
not
your phone out of the way a
All
little
right.
bit. Okay, so in this chemical reaction, I'm going to generate a lot of gas, which again is going to increase the pressure inside of the container. And I've got a little rubber stopper here. So I'm going to put a pile of baking soda on top of this rubber stopper, and then I'm going to cram this down over so it creates a tight seal around here. So this is just a standard pill bottle and a rubber stopper. You could use a cork in the same way. If you used a cork, you could drill out a little hole for a pocket for the baking soda to fit in. I'm going to cram this down on here as fast as I can, and we're going to sit it down on the table, and we're going to see if we can get this thing to launch. So I don't care about amounts here a lot. I'm just going to pile a bunch of baking soda on there so I make sure I have plenty. Baking soda costs 50 cents a container, so I'm not worried about scarce resources there. Just a little bit, maybe a little more than a teaspoon of baking soda. Okay, I'm going to try to go ahead and back the camera up. I'm going to put this on here as quickly as I can without spilling it. This is the tricky part. And stand back. It's getting ready. Oh, come on, little rocket. There she goes. Way up in the sky. So we lost it on the camera, but it probably went 10 feet or so.
10 feet easily. I
Okay.
caught it. I'm not very good at catching things, but I caught that one.
Okay, so let's try this again. I'm going to kick this rocket out of the way over here so I don't trip on it. Let's try this again, and I haven't tried this before, so this is a real experiment. I'm going to use the same amount of baking soda on top of there. And this time, don't drink those bubbles. You'll burp funny. Okay, this time I'm going to add the vinegar, same basic amount of vinegar, but I'm going to add a little bit of bubble solution. So I want you guys, especially you kids, make a prediction what you think might happen with this bubble solution. What's it going to change about the way things go up? I have a prediction I think might happen, but we'll see. And I honestly have not tried this before, so this is the first time anybody gets to see this. I don't even know what's going to happen. See the foam going? And it didn't really do anything.
It foamed up here.
It foamed up inside.
And a little on the launch pad.
So what I think would be fun to do, I would build a rocket like this And I would put a little ring in here, much like the ring that we find inside of the bubble wand. If I can get that out of there with my big fingers. So a ring like this that has some surface tension, and I bet that as it went up,
It blow rings.
it would blow some bubbles as it went. Not many, but
No.
a few maybe. So
Good
just-
experiment to do,
yeah.
the testing you can
a
do.
fun little thing that you can do just to make a little simple rocket at home. Those types of things. Okay, so that was all fun, but let's burn something.
Oh yeah, now we're talking.
Okay,
This should only be done with adult supervision at home, though.
yes. So all of these
Kids,
things,
don't try this by yourself.
we want to reinforce. I'm testing all of these things beforehand. We're doing these things in a very safe, controlled environment. I'm the adult supervising all these people around me. They are crazy. They want to do some amazingly crazy things. Okay, let's bring the camera in right over here, and I'll show you these little rockets that I've built. So I just went online and looked up matchstick rockets, and I found these this template that I used for these matchstick rockets. So basically, all I have here is a standard household match, and I've cut off the heads of these matches and used this little template to make these foil sheets. And then we put the match head inside here, and I've rolled it up in a tube so that we get this nice little tube. Now you can use bamboo skewers or something round like this. Needs to be fairly small. I think that something like a pencil would probably be a little too large. And what I used is this metal rod. So I use this metal rod to roll them because I thought the metal rod would be a little smoother and it would launch. And I get a little carried away, so I made one that has multiple angles. So this is a lower angle and this is a higher angle to launch.
And you can use that to test what will happen differently each time.
We could do different folds in the rockets, different length of rockets. You could try one with 2 match heads versus 1. So there are lots of things that you could test and explore with this idea. So again, what's going to happen here, this would be very similar to what happens in a real rocket. We're going to create a combustion reaction, and that's going to generate hot gases. What do we know about pressure and heat?
Well, when you burn something, it releases heat, and it then increases the pressure on any gas contained in it.
Okay.
So that if it's contained inside of there, it won't expand on its own, and you'll build up this pressure inside that container, just like a balloon would be.
Sure. So if I am containing the gas inside of here, the metal rod is preventing it from escaping, and I've crimped the top of this very good with some pliers. So I took some needle nose pliers and crimped the top because my goal is to keep the pressure in there. We should be able to get this to launch. Okay, now I've used my propane torch today because it's a little bit breezy out here. I'm going to light this match head and we're going to watch it fly off in this direction. So this will heat up the match head, and when it ignites, oh, we got a little dinky burn on that one. That one didn't go very far.
No, it didn't.
Let's try another one. I've got a whole bunch of them.
Was that the Soviet launch?
Now we can't be making fun of other countries.
Well, the Soviet Union doesn't exist anymore.
Oh, it doesn't. Okay, all right. Okay, so here we go again. Oh, those are pretty puny. In my tests, I got these to go like 40 feet.
Oh, really?
Yeah,
I wasn't here for the test.
at home. Everything works better when I do it at home.
Oh, sure.
Okay, this one's gonna go. This is the bane of science teachers. We test all these things and try them really hard.
So it
at
really
home.
did work at home better than it did
Yeah,
here?
let's try the bamboo, just
Okay.
for grins.
All right. You want to take the metal rod out? So.
Oh yeah, that'll be it. You can hear the donkey in the background there.
Maybe he went.
Oh yeah! Oh, there
much
we go.
better, much
that
better.
would have been much better.
That fired
Let's
right
try this
away.
one on there.
That went about 10 feet, 10 or 12 feet.
That one totally petered out.
I guess probably some of them were crimped better than others, maybe.
May have been. The tightness around the rod and all of those things are going to affect it. The friction against the foil and the rod, all those things are going to impact how
Sure.
much pressure we generate. Okay, now it's time for the grand finale. If you've already tuned out, oh, you missed out. But you don't know because you've already tuned out.
Yeah.
So, all right. So what I've prepared here is I've taken some common things that you can find, and I've created rocket fuel. So in this container, it might not look like much, but this is actually a pyrotechnic powder made out of a substance called saltpeter, which is this white salt substance that you see here. Its chemical name is potassium nitrate, the common name saltpeter, and powdered sugar. Okay, that's all that's in this mixture.
You want that rather than granulated sugar?
Yes.
Because it reacts more quickly?
Yes, because, and I've taken this and I've used my mortar and pestle to grind it up into smaller pieces. All right, so when we have a combustion reaction, we need a fuel source, we need an oxygen source, and we need some type of ignition or heat source to make that flame burn. So the fuel source is the powdered sugar. If you eat powdered sugar, it fuels your body.
Yep.
Okay? We talked about that in an episode a couple weeks ago, how the calories in food give our body energy, and we're going to demonstrate that. I actually burned some tortilla chips and potato chips to show that there's energy released as those things burn. So here we're going to burn this powdered sugar mixed with saltpeter. So the saltpeter, the potassium nitrate, has the formula KNO3. The O is the oxygen. So when we launch a rocket, we want the fuel to be inside with the oxygen. There's not enough air in this. If this were my rocket shape, there's not air getting into here. I've got to have air inside the cylinder. So when I think about something like a bullet that we would fire out of a rifle or a pistol, the oxygen it's all sealed inside with the fuel, and it has to burn inside.
And space rockets are the same way. When NASA launches, they've got the oxygen either in form of oxygen or in the form of some other element or chemical,
with the nitrate things.
Yeah.
So this is providing us both a carbon source as the fuel and an oxygen source. Now, I've done this in a very safe way and tested this multiple times. So basically, I've built this little container out of just copper pipe that's soldered together here with a cap, so there's no hole in this end. I put it in here, I fill it up with the powder, and every few scoops I've tamped it down so it's nice and tight. Now, many model rocket users will actually use this type of fuel instead of buying the pre-packaged Estes rockets.
Is it the same if you buy it? It's the same fuel?
It's very similar, but this one is a lot cheaper because I got 4 pounds of potassium nitrate for $12 and powdered sugar is a couple dollars. So I can make a lot of rockets for a little bit of price. The other safety element I've got here, this is a detachable cap. So I'm not making any type of a bomb, which would be a sealed container. This cap will pop off if it builds too much pressure as my safety valve. And there's a nozzle in the end here. What does a nozzle do for a rocket?
It allows the burnt gases to move out, the high pressure gases to move out the end of it to provide the propulsion.
So if there's hot gases being shot out of here, then as Dr. Faulkner explained earlier, that's going to generate momentum in this direction. So I've also got a piece of cannon fuse here. I've measured this. I know this is going to burn for about 7 seconds to give us time to move away. So we're going to insert this into our cradle over here and launch this. Now, to make sure that we're doing things safely, we're going to do this as a static launch today. We're not going to be sending the rocket anywhere, but a static launch. So I've built this little cradle here, and this is going to hold our rocket in a stationary position, but we should be able to see some motion. It's got a little bit of swing in it.
You'll see the exhaust go to your left, and the rocket will tend to go to the right. The wires will pull it back.
Yep. So we're going to make sure this is nice and tight so that we don't have any unexpected launch. And this is a safe area. There's nobody to either side of us. Again, trying to think through all these things and do it wisely and safely to protect people. Okay, I'm going to seat this fuse inside of there. And all of us are going to move off to this side. Again, you might want to grab your phone. I don't think anything bad's going to happen. But we'll move over here. I'm going to light the fuse. We have a predominant wind direction. Help if I turn the gas valve on. And I'm going to move away. and we should see about
Should we give a
3,
countdown?
2, 1.
Ignition.
There's the ignition, and you can see how much that gas is moving in there.
It's pushing the
And
rocket
it's pushing
to the right.
that hot gas out, and the rocket's moving to the right. You can see a little bit of swing in those wires. So if we were to sit this on the ground, it would be able to launch straight up into the air.
Yeah,
You can
quite a
see
long
the
burn.
massive. All right, there was our little burst at the end, and you could clearly see that the rocket moved off to this side. So that's the type of fuel that would be used inside of small rocket engines or even larger rockets that we'd be launching up into space. All right, any final remarks you'd like to make while I check for some questions or comments?
Well, this has been really cool. You know, many of these rockets I'd never seen before. Some of them I have, so my hat's off to you. You did a wonderful job getting together some things. I learned some things today.
All right. I really enjoy doing these things and engaging with you guys, and we're going to continue having these programs, continue bringing more fun science stuff, always trying to help you understand more about how God's created the world and bring Him glory in all of those things. And until we see you next time, go out and enjoy God's amazing creation and explore all He's made for you.